Hello and welcome to decodingpacket.info's MVPN video series. In part 1 of the series, we discussed some of the basic MVPN options and we concentrated on how Rosen GRE worked inside the provider core. Well, now it's time to actually configure and understand how the different pieces of it fit together, what parts would go on CE routers, what parts would go on PE routers. If we need to do anything with the core, we would be carrying out these configurations on iOS and iOS XR devices. Now, curiously enough, Cisco chooses to call this profile 0 in large parts of their documentation. So if you're following along with any of the documentation, then this is profile 0 that we are talking about. It's also called GRE-based MDT, and we will be using Any Source Multicast in the actual core. Now, just a quick recap. There are always 3 parts, or 2 parts if you look at it, of any MVPN. The first part is how does the CE signal anything to the PE? So in this case, you can see that both of the CEs to their respective PEs run PIM. So they're PIM adjacent and PEs are going to run this PIM inside the VRF. The CEs usually would be running it in the global routing table or the global context. The second part is what is the signaling used between the 2 PEs? So what is the signaling that is overlaid onto the provider core? In this case, CPIM is overlaid on the provider core. So the PEs, all of the PEs in our context are going to be adjacent to each other over CPIM inside their VRFs. And we are going to see how to configure this on iOS. Finally, there's the question of the transport. So how do you transport these packets? So control packets for one, but ultimately, how do you transport data packets across the provider core? Well, as we discussed with Rosen GRE, you use multi-point GRE tunnels. So these are GRE tunnels with destination addresses that are multicast groups. And ultimately, these tunnels are going to be signaled using PPIM, which is provider PIM. So yes, in this particular option, you would have to run PIM in the provider core to facilitate the building of these MP-GRE tunnels. Now let's take a quick look at what different pieces do we have to configure and then step by step go ahead and configure them on our devices. So the very first thing, VPN v4 must be fully working between all of the client sites. So if you have 1, 2, 3, or 4 client sites, they must be already configured for VPN v4. Their PEs should be redistributing all of the right information, and they should have full connectivity to each other and to the PEs. The major reason for this is RPF checks. So if you realize the multicast routing protocols always use unicast routing tables for RPF checks. Now, those RPF checks, especially on the PEs, are going to be inside the VRF and they're going to use this VPN v4 information, but also inter-site. So if you're doing an RPF check between 2 sites, source is on one side, a receiver is in the other side, or a rendezvous point is on the other side, you also need to have that information to perform your RPF checks. So VPN v4 must be fully configured and working. The second prerequisite here is that PPIM must be fully working for Any Source Multicast. So your provider core must already be set up for provider PIM. And don't worry, our provider core is not right now set up for this, so we will show you exactly how to go ahead and get those pieces to work. This is not any different than how you would set up multicast in any enterprise, but it's just being done in the provider core. So the 2 things you have to be absolutely sure about Any Source Multicast is that the RPs are well defined. They know that they are RPs, and their information is disseminated to all of the routers. So all of the routers agree on who the RP is, or RPs are. And finally, the multicast data plane must also be working. So let's go ahead and see if these prerequisites are already applicable on our particular topology. So for this lab, or for this configuration, this is the topology that we are going to use. Now the provider core is right there in the middle. It consists of R1 to XR1. So R1, R2, R3, R4, R5, and XR1 together form the provider core. R1, R4, and XR1. So these are your PE routers. R1, XR1, and R4 are all PE routers. Everything else is just playing the part of a P router. Now there are three sites. Site 1 that is connected to R1, Site 4 that is connected to R4, and Site 21 that is connected to XR1. The core is already configured with ISIS and LDP. So this is already working. And like I said, VPN v4 is also working. So VPN v4 between these three routers, that and there, VPN v4 is also functional. And finally, we have reachability end-to-end. So let's go ahead and test out some of that reachability. What we will do is we'll pick R7 and we will try to trace our route to R9. Now the loopbacks in this are really easy. They don't make much sense in the real world, but in the case of our lab, they make perfect sense. So all of the loopbacks are in the form of XXXX, where X is the router number. So for example, R7 would be 7777, R9 would be 9999. In the case of XR, you just add 20 to the value. So in this case, for example, XR1 is 21 and XR2 happens to be 22. But let's go ahead and trace a route from R7 to R9 and see how that is going to work out. So here I am on the console, and let's go ahead and connect to R7. And first, let's see if there is a route for R9 in the routing table. So we'll say do show IP route 9999. And there is a route. And let's go ahead and let's trace that route. Do trace 9999. And we're going to use the source address of the loopback. So source loopback 0. And let's pull the topology up again to see what path it actually takes. So once again, you can identify the router by the last octet. So in this particular case, this is going from router 6. So right here, it's going from router 6, which is connected to, which is inside the site. So this is router 6. Then it is going from router 6 to router 1, which is connected to the PE, or which is the PE in fact. R1 sends it across the core. So it uses, in this case, R2. It has equal cost multipathing, but it uses R2. And you can see there are two MPLS labels on that. There is a transport label and a VPN label. R2 sends it over to R4, which is this way. So once again, it had equal cost multipathing options, but it chose R4. R4 sends it over to 21, which is down here. And 21 sends it into site 21, which is R8. And then finally, it reaches R9. So this way, and then finally over there. So that's the whole path that the route is taking through the provider core. Let's just for connectivity's sake, let's take one more trace route here, which is going to be to 10.10.10.10, which is basically a stub router in site 4. So we'll say do ping 10, 10, 10, 10, or actually it should be trace. Do trace 10, 10, 10, 10, and we're going to say source loopback 0. And once again, you can see it goes to router 6, number 1, and then to router 1, to router 2, to router 4, into site 4 to router 22, which is XR2, and then finally to router 10. So our VPN v4 is completely functional in this case. The other thing that is functional here is that between all of the sites, so between site 1, 2, and 21, so within site 1, site 21, and site 4, PIM is fully working. So we have PIM, And what we have is we have IP multicast routing, we have PIM on all of these interfaces, and we have PIM enabled on the interface facing the PEs. And that is true with all of the sites. So there is PIM working here, and then there is PIM enabled on the interface that is facing the PE. The PEs, of course, are not set up for PIM yet, but the sites are. And finally, the sites don't really have connectivity to each other, but we are also going to configure R6 as our CRP, because remember, there are going to be two separate trees here, so we have to keep an account of which particular topology we are talking about. So there's going to be a PRP, but in this case, there is a CRP, which happens to be R6. And what we have to do is, using BSR, we have to get this information over to site 4 and site 21. But because BSR works on PIM, that's going to be one of the first things that should come up once we can establish PIM adjacencies over the provider core. So now the next task here is going to be then to get multicast up and running inside the provider. So for this, it's going to be on all of the iOS routers, and in particular R5, or let's do this, R5 is going to be the PRP. So for R5, we're going to choose that as a PRP, and we are again going to use Bootstrap Router to disseminate that information throughout the PIM network. So basically, you should understand what all of this entails. So we have to, number one, enable the multicast routing process on all of these routers from R1 to R5 plus XR1. And we have to enable PIM Sparse-Mode on all of the relevant interfaces, which literally means every single interface. So let's go ahead and do that. So we'll start off with R1. And actually what I'm going to do is I'm going to cheat my way through this. I'm going to send the commands to all of the iOS routers all at once. And what I'm using for this is this little cheat window here. So what's going to happen is I'm going to say IP multicast routing distributed. And what that does is that essentially starts the multicast routing process on all of these iOS routers. And it looks like it didn't take here, so we'll say IP multicast routing here separately on R4 distributed. But essentially it has to be on all of the iOSs. We'll deal with the XR later. It's a little bit different way of doing things on XR. But first, let's take care of all of our iOS routers in the core. The next thing is I have to identify all of the interfaces that are going to be running PIM. But at the very least, I know all of the loopbacks are going to be running PIM. So I'll say int loopback 0. Once again, I'm cheating my way, sending the commands to all of the sessions. And I will say IP PIM Sparse-Mode. And that means it should now be working on all of the loopback interfaces. Let's check a couple of them. So that means it's working on all of the loopback interfaces. The next thing I need to do is enable this on the physical interfaces. To enable PIM on the physical interfaces in iOS is obviously going to be a real pain. And I'll show you one. I'll pause the video and then I'll go ahead and enable it on all of the other routers, and then I will restart the video. So let's take a look at how we would go on doing it on, say, R1. And again, from a CCIE perspective, you want to be really fast at doing this. So first we have to identify all of the interfaces in the VRF. In the global routing table, not in the VRF. So we will say do show run include. So I would say something like caret interface. So any line that begins with interface. Now for me, all of these interfaces, so dot star, any string in the middle, all of these interfaces are gigabit Ethernet 2. So instead of doing that, I'll say 2, and then they are all sub-interfaces. So that makes the dot explicit. So what this regular expression is doing here is it's finding all of the interfaces for me. Out of those interfaces, I just have to leave out the one that is running in a VRF. So that decision is mine. So in this case, it's going to be towards R13, so R3 and R6. So once again, keep the topology handy as I go through this. But if you look at this, R2 and R3 are going to be the two routers that are going to be relevant, and R16 is going to be the one router that is inside the VRF. So R2 and R3, that means 212 and 213. So what I usually would do something like this is I will take it into a text editor, and then I would say IPPIM Sparse-Mode, and then copy that and then paste it again. And then take this entire config and paste it back into R1. And now I have enabled PIM on all of these interfaces. So why do it inside a text editor? Is because when I go to R2, my job becomes easier. Now I have 4 interfaces to do here, right? So all I need to do is change the numbers on here. So let's take this, there are 4 interfaces, so I'll copy this and paste it back again. So now I have 4 interfaces. Now one of those interfaces is the same, the other ones are 23, 24, and 25. So this would make my job a lot easier. I take this and I paste it back in. It's a pure P router, so we have all of the interfaces. So now I will pause the video. I will finish this on the rest of the routers, and once I'm done and ready to go to XR, I will come back. So as promised, I've gone ahead on all of the iOS routers, R1 to R5, and I have enabled PIM sparse mode on all of those interfaces. And I've also issued the command show IPPIM neighbors to see if all of our neighbors are consistent. So R1 is connected to R2 and R3, that looks good. R2 has 1, 3, 4, and 5 as its neighbors, so that also looks good to me. So R2 has 1, 4, 3, and 5 as its neighbors. R3 has 1, 2, 4, and 5 as its neighbors. That looks good. R4 has 2, 5, and 3 as its neighbors. Its other neighbor is XR1, but remember we haven't configured XR1 yet, so 3 neighbors looks good there on R4. And on R5, it's going to be the same story. I have 2, 3, and 4, but no XR1 yet because I'm going to now configure XR1. So this is just repetitive stuff, but we have to basically get PIM working on all of the core links to avoid any issues. Now on XR1, it's going to be a little bit different configuration. So let's go to the root of XR1. And the way XR1 is going to be started, it's going to be actually easier than iOS. What I can do is inside multicast routing address family IPv4, I can choose the interface option. So which interfaces to enable multicast on, and that basically means PIM sparse mode in the context of XR. And I have an option which says interface all. So all of the interfaces that are in the global context, enable. And once I commit this, I should see that my neighborship on R4 and R5 should start coming up. So there we go. I see some activity on R4 and R5, and they have now detected a change in the DR, and they have detected a new neighbor on for XR1. So R4 and R5 are now adjacent to XR1. So it's a simple command on XR1, but it's relatively important. So on XR1, I would say do show PIM neighbors, and I should see 4, 4, and 5 as my neighbors, and then I also have it enabled on loopback 0. The last thing I have to do here is to go to, and what did we decide to use as the RP? It was, I believe I decided R3 to be the RP. So I will stick with that. I'll go to R3. I hope it was R3. I've kind of forgotten, but R3 looks like a good candidate for the RP. So I'll configure it as the BSR and the RP. This is not a multicast lab, so we are going to keep things as simple as possible. Now, from that point of view, static RP would have been the simplest, but that involves a lot of configuration. With BSR, we also get to know if our core is sort of functional, because if we see the information disseminate on all of the routers, that implicitly sort of confirms that our multicast core is doing good. So on R3, I would say IPPIM RP candidate, and I would say use loopback 0 for the RP candidate, and I'll make it for all of the groups. And I would also make it a BSR candidate, loopback 0. So the first thing I should check on R3 is do show IPPIM RP mapping. And I see that now 3333 is advertising itself as an RP for the entire multicast range, the class D. Let's check it on all of the routers at once. So we'll say do show IPPIM RP mapping. And on R1, it seems to have received that information. R2, R3, R4 has that information, and R5 has that information. Now, luckily enough, this command does work on XR2, but the actual command we should have used on XR should have been do show PIM range list. So that shows you a different version of this, but it's also backwards compatible with the RP mapping. But either way, make sure that you confirm. What the range list also shows you is that XR1 is SSM enabled, which would be useful in our next lecture. So now what's happened here is our core is completely working with PIM. And that is good news because that's what we were trying to do. So VPN v4 completely working. PPIM is now completely working because we have the RP defined and disseminated, and our multicast data plane should be working. I haven't tested it out yet, but we would let our C sources and C receivers check that out. If they can get through, if we can form the GRE tunnels, if we can get the PIM adjacencies, then that would implicitly confirm that my multicast data plane is working. I have no reason to believe that it is not working, so I'm going to skip that verification for right now. The next thing here now is going to be activate CPIM with the PE VRFs, because if you realize the PEs and the CEs run CPIM between themselves, and the way to activate CPIM on a PE, because remember PE is also running PPIM because R1, R4, XR1, they're all running PIM globally. So to activate CPIM on them, it actually has to be done inside the VRF, just like any other routing protocol. So in this case, the configuration is fairly easy again, but as long as you keep track of it and verify your work, this should not be that difficult. So let's go ahead to our PEs. So our first PE is R1. And on R1, you're going to do two things. So remember IP multicast routing command? Now it has to be activated for the VRF. So this VRF in this particular case is called C1, customer 1. And some platforms are going to take the distributed version of the command, others are not, but see, it's not going to let you complete the command without distributed if it needs distributed. So if it gives you an error, always say distributed. So IP multicast routing VRF C1 distributed. That's the first part. The second part is going under the VRF interface. So if I say do show IP VRF, I need to go under this interface and enable PIM sparse mode. Now that doesn't have any VRF related commands to it, but if you look at the interface itself, it is already in a VRF. So if I put PIM sparse mode on it, it is automatically working inside the VRF. So I'm going to go to this interface and I'll say IP PIM sparse mode. And believe it or not, that is it. That is it for enabling CPIM on a PE. So I'm going to repeat this on R4. So exit, so I'll say again IP multicast routing for VRF C1 distributed. And then I'll say do show IP VRF. I'll go under this interface. I'll go under that interface and I'll say IPPIM Sparse-Mode. So once again, I should see that my adjacency should come up. I didn't make a note of that here, but if you see, the VRF PIM adjacency did come up on R1 and it has now come up on R4 as well. Finally, how to do it on XR1. So again, XR1 is going to have a different way of doing it, but again, it's going to be fairly simple. The command again is multicast routing, but instead of doing it globally, now I'm going to do it under the VRF. So I'll say multicast routing VRF. The VRF name is consistent everywhere. It's C1. And which address family am I doing it for? So it is address family IPv4. And remember the interface all enable command? That also applies here. So I don't have to think about which interfaces. I can literally just say interface enable or interface all enable. Once I commit this config, in a couple of seconds here, I should be able to say do show PIM VRF C1 neighbors. And there we go. Those are my VRF C1 neighbors. We should issue the same command on R1, although the logging message did confirm that. I should say do show IP PIM VRF C1 neighbors, and I should be able to see the neighbor. Let me take the same command out to R4. And now we have this working. Now, one of the things that I didn't do, so if I look on R1, if I say do show IP PIM VRF C1 RP mapping, I wouldn't see anything yet, because one thing I neglected to do is I haven't configured a VRF. I haven't configured an RP on my CPIM yet. So on one of the sites, I have to configure an RP, and I believe we decided that it was going to be R6. So R6 is going to be my RP. So let's go ahead on R6. We're going to do the same exact thing. We will say IPPIM RP candidate, loopback 0, and it's also going to be the BSR candidate, loopback 0. And what should happen is within site 1, which R1's VRF is part of site 1 when it comes to CPIM, everybody should now have this information. So on R6, R7, and R1. So let's note that again. On R6, R7, and the VRF of R1, I should be able to see R6 as the RP. So let's go ahead and verify that. So on R6, I'm going to say do show IPPIM RP mapping. And there we go, it's 6666. On R7, I don't really have much doubt. It should be working. IPPIM RP mapping. So this is also working. It knows 6666. And then on R1, this has to be within the context of the VRF. So I'll say do show IP PIM VRF C1 RP mapping. And there we go. Now it's not going to propagate to any of the other sites because PIM right now within the sites is broken because there is this big giant provider core in the middle that is not running any CPIM. So the next task here now is to create that multi-point to multi-point GRE tunnel or point to multi-point GRE tunnels between all of these devices and get that CPIM message tunneled across to all of the PE routers that it needs to go to. So literally the only thing that we need to decide for that is a group. So once we decide and configure that group on all of the PE routers, so yes, PE routers would have to be configured with that group. But once they are configured with that group, they then know that they need to form a GRE tunnel with that group as the destination, and they need to listen to that group for incoming GRE messages, and that's how they will become PIM adjacent. So this part is not very hard, but you just have to remember to do it. So in our case, let's pick a random group. 239.1.2.3 happens to be my favorite group. So what we will do is we will configure this as the default MDT. So again, remember, Rosen GRE is now called default MDT or MDT, but default is the point to multipoint or multipoint to multipoint tree where all of the PE routers are. So what's going to happen here is all of the routers do not know who the sources are yet. How can they, right? So they're not aware of each other. They don't know who wants to take part in the MVPN. So with this group, they're then going to form star comma G trees. And they're going to join those star comma G trees towards the RP, which happens to be R3. So R1 is going to signal a star comma G to R3. R4 is going to signal that star comma G tree to R3. And then XR1 is also going to signal that star comma G tree hop by hop to R3. So R3 being the rendezvous point should then get all of these messages, but at the same time, they will also create a GRE tunnel and start sending messages this way. So they will start then sending messages out to that group, which then they will register themselves as a source with a unicast register message to R3, and then R3 should turn those messages around and send it to the destination. That is the beauty of Any Source Multicast, right? The RP just kind of brings everything together. But at the end of the day, you should have one star comma G, and then because there are three routers, you should have three S comma 239 1 2 3 states on many of these routers. But that's how it is going to work. So once again, with iOS and iOS XR, there are two different places to configure this. Let's go ahead and see what those places are going to be. So with iOS, it's going to be under the VRF definition. So we will say VRF definition C1. Let's take a look at this VRF2. Do show run VRF C1. So that's our VRF right now. And where you configure address family IPv4, that's exactly where, along with the route targets, you configure the MDT default group. So let's go ahead and take a look at it. Address family IPv4. The command here is going to be MDT, so multicast distribution tree. We are trying to configure the default MDT tree. We are not using MPLS yet. We are using GRE. So all you have to provide it is an IP multicast group address. And that address happens to be, that's right, 239.1.2.3. So I'm going to physically put this in, 239.1.2.3. And believe it or not, that is all that is needed for this. So you can already see it created a tunnel called Tunnel 2. It has also started PIM on that particular tunnel, but that particular tunnel is running PIM inside VRF C1. So now if I see do show IP PIM VRF C1 interfaces, I see Tunnel 2 as one of those interfaces. Let's take a look at the salient features of Tunnel 2. So if I say do show INT Tunnel 2, it shows me that this is a GRE tunnel. So hardware is tunnel, it's GRE. And it is a multi-point GRE tunnel. And let's see if I can see the destination address anywhere. It usually is visible somewhere here. It is the tunnel source is loopback 0. I am not able to see, it may be just staring me in the eye, but I'm not able to see it. But the tunnel destination is going to be 239.1.2.3. Furthermore, what you can see, or what you should be able to see here, is in the mRoute table, the global mRoute table, because remember the tunnels are being built on PPIM. So in the global mRoute table, I should see star comma G for 239.123. So if I say do show IP mRoute 239.123, there we go. I have a star comma G for 123. It is the it's going over to the RP3333, and the incoming interface, the RPF interface, is the one connecting me to router 3, which makes sense. So that's the RPF interface towards my RP. But look at the outgoing interface list. It's not in the global VRF, but it is in the MVRF or Multicast VRF C1. And that's tunnel 0, even though it doesn't state it here. So I'm also sending packets. I've registered myself to the tunnel, to the RP as a potential source for this. So both of those things have come true. Let's go ahead to R4 and do the same exact thing. So we will say VRF definition A, address family IPv4 unicast, MDT default, and then I just have to configure the group 239.1.2.3. So there we go. Tunnel 1 is now up. I've also configured myself as a DR on that particular tunnel. But it doesn't look like my neighbor is coming up yet. So on R1, actually it has. So on R4, R4 is the actual DR. So it just changes from 0 to DR. But if on R4, if I say do show IPPIM VRF C1 neighbors, or no, so this is not going to be, it seems to be a unidirectional tunnel here. Let's take a look at it from R1. R1 is definitely receiving these messages, right? So do show IPPIM VRF C1 neighbors. So on R1, I'm definitely getting messages from R4, but it looks like it's a unidirectional thing right now, because do show IPPIM VRF C1 neighbors. I'm not seeing R1 as a neighbor. Now, the way I'm going to troubleshoot this is I'm going to troubleshoot this in the global multicast routing table. And the very first thing I would have to do is see if I have an RP. So I'll say do show IPPIM RP mapping. I have an RP, it's towards 3333. The next thing I'll have to do is to see if I'm creating a star comma G tree and if I'm registering myself with the tunnel. So I'll say do show IPPIM or IPM route VRF C1 239.123. Sorry, so it's going to be in the global routing table. I'm confusing myself by looking at CPIM. But here we go. So I have 239.123. That looks good. I do have an interface that is joining that tunnel, but I don't really have an outgoing interface. So I have nothing in my oil, whereas if you look at R1, you have to have that tunnel interface in the oil. So something went wrong with the configuration. Let's take a look at the VRF itself. Do show run VRF. So that VRF looks good there. And that's my problem. So I have Creature Fabbit, I've created a wrong VRF here. So let me get rid of that VRF. I'll say no VRF definition A. So that's gone. And what I'm going to do is in VRF definition C1 under the address family, I'm going to again have to create this. So now hopefully we have more success. We have tunnel 1, change the state to up, DR has changed. So now let's see if we have a PIM neighbor. Do show IPPIM VRF C1 neighbor. So the neighbor still has not come up, but now it looks like it might have come up. Nope, so still tunnel 2. There we go. So it took its sweet time, but now neighbor 1.1.1.1 is up on tunnel 1. So basically this was the configuration that was needed. I was just doing it under the wrong VRF. So now if I do my pim neighbor command again, I will see that 1.1.1.1 is a neighbor on tunnel 1. That means I have a multicast GRE that is bidirectional. I have one from R4 towards R1 or towards that group which R1 is a member of, and I have a multicast GRE from R1 to that group which R4 is a member of. The last thing that I would have to check here before I move to R1 is I have to see if my RP, the BSR information, has disseminated over the core, and R4 should now be aware of R6 in the context of C1 as an RP. So I should say do show IP PIM VRF C1 RP mapping. And there we go. Now you can see R6 is known as an RP to R4. And this can only happen across the SP core. So this is now happening across the SP core. What that should lead to is XR2 and R10 should be aware of this RP now. So let's go to XR2 really quick. Do show PIM range list. And there we go, 6666 is known as an RP now. And finally on R10, do show IP PIM RP mapping. And looks like R10, is R10 the right router? Yep, R10 is the right router, but it doesn't know about the mapping yet. Do show IP PIM neighbors on R10. And it looks like R10 has just not been configured. So let me see, do show IP PIM interfaces. And yeah, I just haven't configured PIM on the interface connecting XR2 and R10. So let me quickly take care of that. So I'll go to this interface, which is this one, 1022. And I'll say IP PIM Sparse-Mode. So hopefully as that neighborship comes up, which it should shortly, there it is. Soon I should also be learning about the RP mapping. So I do show IP PIM RP mapping. I'll give it a couple of minutes here. Sometimes it takes a little bit of time for that information to disseminate, but at least we figured out what the problem was. Now the final thing here is going to be to configure this on XR1. So once again with XR1, the MDT configuration is going to go in a different place because on XR1 we like to, or XR generally, we like to do things differently. So we will say do show IP so where is it going to go? It's not going to go under the VRF. That's for sure. So it will go under the multicast routing instance of VRF. So show run multicast routing. It's actually going to go inside here. So multicast routing, VRF C1 and address family. So that's how they chose to do it, but you just have to remember it. Multicast routing, VRF C1, address family IPv4. And now here I can say MDT default. The rest of it is pretty similar. Although, so you can just go ahead and straight configure the address, or you can use keyword IPv4. It doesn't matter. Let's do it exactly the same way we did it on R1 and R4. So MDT default 239.123. Now, there's one major difference here. With R1 and R4, you do not have to choose the, they basically pick the BGP update source. So how did R1 and R2 decide which interface to use as the tunnel source? So obviously you can see that they're using their loopbacks as the tunnel source, but where they're getting this information is from the BGP configuration, because I have update source loopback 0 and BGP. So that's where they're picking up that information from. In XR1, I have to specifically provide that information. So in addition to the MDT default, I would have to say MDT source loopback 0. This is very often missed. This is probably the #1 reason of a lot of problems on iOS XR. But in our case, we remembered it and we are going to say commit. So once we commit this, hopefully the tunnel goes up. Hopefully I haven't missed anything. And there we go. You can see R4 now sees XR1 as a neighbor. R1 now sees XR1 as a neighbor. But more importantly, let's go on XR1. And let's go to the root and we'll say do show PIM VRF C1 neighbors. More importantly, XR1 now sees 1111 and R4 as its neighbors. Now it's not calling that interface a GRE tunnel, it's calling it an MDT, and it's appending the VRF name there, but that's just a data structure. So ultimately what's happening is exactly the same thing. The PIM messages are being sent encapsulated inside the GRE. So the last thing here, let's see if the RP has disseminated. So we'll say do show IP PIM RP. So it's actually going to be do show PIM VRF C1 range list. And there we go. The RP information has carried itself all the way to XR1. So the final 3 routers that we have to verify are R10. So we were in the middle of verification here. Let's go ahead and see the RP mapping. R10 looks happy. We have to look at R8 and R9. So on R8, we'll say do show IP PIM RP mapping. That's good. And R9, do show IP PIM RP mapping. So that essentially now means that the CPIM is carrying my the PPIM is carrying my CPIM messages across the provider core. All of the sites agree on who the rendezvous point is going to be. And the final verification here is going to be if I join a group. So for example, on R10, I will go ahead and join a group. That's pretty much the only way, because in an actual network, you will have sources and receivers, but I will make him a receiver on the loopback for, let's say, a different group. I don't want to confuse everybody, so I will say let's pick 239.1.1.1. Now this is a C group. You have to remember that. So the 239.123 was a P group, but this happens to be a C group. And once we join this receiver on here, I'm going to send some pings. I'm going to make R9 the sender for this group, or it's going to be a C sender for that group. And if I can get the replies back, that means my core is functional and everything is working like I expect it to. So let's go over to R10 and create a receiver. So we are going to simulate a receiver by sending some IGMP joins, and we are going to join that 239.1.1.1 group on loopback 0. So this would be interface loopback 0, IP IGMP join group 239.1.1.1. And the quick way to verify is to go to the upstream router, which is going to be XR2 in this case, and do a quick show PIM topology on 239.1.1.1. And what we should see is a star comma G join that is going towards 1022, and then upstream it's going towards the SP core. So R10 seems to have successfully joined. The next part here is going to be sending some PIMs from R9, and R9 is going to send these pings towards R8 on the same address, and R8 is then going to send them, so R8, so what it's going to do is it's going to send some pings. Now, depending on who the DR on this particular link is, that DR is going to then send a register message off the link to the RP, and then RP is already signaled for that star comma G, and it's going to relay that message, and after that regular PIM takes over. Now, in a lot of, from what I've heard from others, and I've never really witnessed it myself, sometimes it does matter who the DR on this is. So in a real network, you'll have actual real senders, and this won't be an issue, but now you're using a multicast router to send pings to a multicast group. From what I have noticed, it's really not a problem. So for example, R9 is the higher IP, so right now it should be the DR on this link, and you will see I will send pings out of this particular interface, and R9 will take over the registering responsibilities and send it over to R6. But in case you run into a problem where the pings are just not going through, try to change the DR to the other side. Maybe it'll work, but I have never really encountered that issue at all. So in this case, what I'm going to do is I'm going to send an extended ping on IP 239.111. I'm going to go with a high repeat count, about 10 should suffice. The timeout is 2, that's fine. Extend commands, yes. Now, this is going to go out of gigabit Ethernet 89, so 2.89, and I think you still have to put the whole interface there. And the source address is going to be loopback 0 or 9999. So let's send this ping off. And that first one does not really go through. So it doesn't look like it is doing anything yet. Let's go upstream to R8 and check for the mroute table. So do show IP mroute 239.111. And that group has not been found. What about on R9? Show IP mroute 239.111. And again, that group doesn't look to be there. What about just the regular multicast routing table? So it doesn't seem to have done it. Now, sometimes I have seen that problem with extended pings. Let me do this. So I'll say ping 239.111. And I'm going to repeat 10 and source loopback 0. So let's see if that works better. And as you can see, that does work. So that DR problem may be an extended ping problem. I don't really know, but just look at the show IP mroute here, and you will realize that there is an S, G here. So it is treating itself as the DR. It has registered that address to the RP, and then the RP joined the two trees. You see that initially there were 2 replies to it, and then to the first ping. And actually, the first ping did not get a reply. The second ping did get replies. But the subsequent pings, what's happening here is you're sending 2 packets out. You're sending a packet on behalf of loopback 0, and you're sending a packet on behalf of gigabit Ethernet 2.89. But as long as you can see something there and the trees form end to end, then you can be pretty assured that your multicast delivery is working. So that's about the test of this. Let's go back to see what else did we have to do. So we've already done this. We selected one ASM group, we configured it in iOS, we configured it in iOS XR. And finally, when the PEs became adjacent, we did our verification, and that was the end-to-end multicast. Now, finally, there's one thing, and this is also in the Cisco documentation, and it seems to be a big issue. But with ASM groups, you really don't need BGP signaling. So if you look on the routers here, and if I go to R1 and I say do show run section R BGP, the only address family I am exchanging with my neighbors is VPN v4. So there is an address family MDT, but we will realize that that becomes useful for SSM group. So for ASM group, since you have the rendezvous point to bootstrap everything, you really don't need BGP to do the bootstrapping for you. With SSM groups, it's absolutely necessary, but that is something we are going to be covering in our next lecture. So in our next lecture, we will see how this whole topology can benefit with the use of SSM and also on demand trees. So stay tuned for that one. But as for this one, I'm going to wrap it up. It's getting rather long. And yes, we didn't decode any packets, but I will do a separate lecture where I will show you the packet captures and how the information is carried in there. Thank you very much for joining us today.